So today we'll see the very important topic Miller's capacitance. So what is a Miller's capacitance? So today I'm going to explain the Miller's concept with the common emitter amplifier circuit. Before that I'll just give the idea about what is a Miller's capacitance. Actually the Miller capacitance was identified in 1920. The researcher John Milton Miller he identified in 1920 in triode vacuum tubes. So what is that actually? The Miller's capacitance it's nothing like a parasitic capacitance. It is happening in between the input terminal and output terminal. So let me give some idea. Okay, so you take on system, this is a system. So you have an input terminal and you have output terminal. So this is some active device. It may be like a BJT or a MOSFET or a diode or anything. In between this, you have some passive elements, right? Let me take this is as our C mu, like a reverse bias capacitance. So it is connecting between the base and collector. So now thing is I want to identify what is the impedance of base with respect to the input terminal, and also I want to find like this. So what is the individual reactance of this capacitor in the input port as well as in the output port? So in order to find the exact reactance of the port for port 1 and output port, so Miller suggests some idea, that is a Miller's theorem it comes. Okay, so what is the main limitation So it will limit the gain at the higher frequency. Even it is a very small value, parasitic value, it will be multiplied with your some current parameter and it will dominantly work in a higher frequency and it will push your gain down. So you have to be take care of when you are designing the Miller's capacitance. When you are designing any circuit, you want to limit your Miller capacitance in your circuit. That you have to be very careful. So what you are going to do is we are going to put a common emitter circuit and we are going to analyze what is your Miller's capacitance for the common emitter amplifier circuit, and we have a corresponding derivation part. Okay, that is the objective of this today lecture. So here you can see I have taken the common emitter amplifier circuit, and I'm sure you are good in that part, right? We have seen so many lectures. So you have a biasing resistor R1, R2, you have RC resistor, RE resistor. Regarding the capacitor, you have an input coupling capacitor, you have output coupling capacitor, you have a bypass capacitor, you have a load resistor, you have a DC supply, you have a source resistance in parallel, and you have a source current and you have a load current. So you have output voltage V naught. Okay, so here so I said already the Miller effect is called as feedback effect because ultimately the Miller's is coming in between your input and output, so it is something like a feedback. So that's why the same name said the Miller effect or feedback effect. It is a multiplication effect of C mu in circuit application. That's what I said in the last slide. So it is a multiplication effect of C mu in the circuit application, and it should be limited in the circuits. Okay, so especially the higher frequency dominantly will play the major role, so it should be removed certainly to avoid the any non-linearity in the circuit. Okay, so that is the next part. Okay, we are not going to see how to remove, we are going to see how what is the effect, what is the individual reactance of C mu in the base part and the collector part in the coming slides. Okay, so here from this I have drawn this model. From this I have drawn this model. I hope this is clear. I will teach this part. So before when you are drawing the small signal model, you want to remove the VCC and short circuit the capacitors, right? So coupling capacitor and bypass capacitor. So this, let me take, this is your emitter, right? This is your emitter terminal. So emitter terminal. Okay, so then you have your R pipe, that is a forward bias resistor and forward bias capacitor, and this is the reverse bias capacitance. The reverse bias resistance is open circuited, right? So here you want to be very clear. I used a simplifying model. I used the simplify model. So when you speak about a higher frequency part, you have two model. One is the expanded model, another is the simplify model. The simplify model, you will be removing few resistance and capacitance. Those values are very small. Like we will be removing RB, and we will be removing REX. Then we will be removing RC. Then we will be removing R mu. Then we will be removing CX, and we will be removing R not L effect. See this part and then removed, and we will make it like we are drawing like a simplified model. So this is a simplified model, right? So with that only I am explaining. So C mu is your reverse bias capacitance, and GMVP is your current source. It's a current source, okay? It's a dependent current source, and this is a mathematical, so, right? So you have to be very clear. This is your mathematical modeling, right? This is your mathematical modeling for a transistor. If you have, this is your mathematical modeling for a transistor in the higher frequency simplified mathematical. So your transistor only drawn like this, right? Your transistor only drawn like this. So this is your base, and this is your collector, and this is your emitter. So your transistor only drawn in terms of higher frequency with respect to the transistor capacitance and parasitic, because you are studying for higher frequency part. That's why I'm taking the higher frequency capacitance like a parasitic, stay capacitance, and transistor capacitance. I'm considering, I'm doing my analysis. So the in the outside region you can see these are the external capacitor R1, R2, like a this capacitor will become the short circuit, and you have a load current. You can see the source current. So source current is coming to the picture, and your RS is your the signal source resistance. Okay, there is a source resistance, so very less. Okay, so this is parallel to R1 and parallel to R2. Okay, RS parallel to R1, R1 parallel to R2. Okay, so then when you remove this VCC, this RC will come parallel to the RL. So you will be getting like this, right? So you please understand, when you remove the VCC, the all elements will be connected to the ground. Okay, this capacitance will be short circuited, right? It will be short circuited with this model is drawn. Okay, so now same model only. I have increased the size and I given for your best understanding. So I hope this is clear, right? So this is, I hope you just go through it. So the problem is this CMU. The problem is CMU, it is connected in between the base and collector. So this making this circuit as a complex part, right? So to reduce this complexity, that means I want to find what is the impedance of CMU with respect to the base part as well as in the collector part. For that I am going to apply the Miller's concept. Very simple. So see here that what I am going to do is I am going to take this part. Okay, I am going to take this CMU. Okay, so here in the left side, this V pi, that is a drop in your input part, and the output side the drop in your V naught. So the current across, I will take it as I1, and current across this part I will take it as I2, and going to proceed the Miller's theorem. See, I have redrawn as a that C mu in two port network. I redrawn your C mu capacitance in terms of two terminal network. That is a two terminal network of your capacitor. This is your terminal 1, this is a terminal 2. The terminal 1, it is designated as I1. That is, a terminal 2 is designated as I2. The corresponding drop is V pi and corresponding drop is V naught. So ultimately the ultimate thing for this derivation part is you want to find the current gain. That is our principal idea behind this derivation part, right? So A is equal to output current by input current. That is a gain formula. Output current by input current. So now very simple. What I am going to do is we have drawn the two terminal network of the capacitor C mu, and I am going to apply the KVL in the clockwise as well as in the anti-clockwise. Then I am going to draw that equation in terms of model, and I am going to fit that model into the your simplified model. With that I am going to proceed. Very simple. So just follow the slide, you will understand. Apply the KVL in the clockwise. So when you apply the KVL in the clockwise, what you will get? You will be getting a V pi minus 2 plus V pi. Okay. Then we will be getting this for C mu. What is the C mu in terms of current? If you in terms of voltage, if you, because you are applying KVL, right? So that is a you want to find a voltage corresponding to this capacitance. So that is I divided by I into, so you want to calculate I1 divided by j omega c mu. So that is a part, it is coming across this for this clockwise direction, right? So the current across this c mu is I1 into your reactance is j omega c mu, plus entering at a plus, leaving at a minus. So please understand, I am applying the KVL by considering the living symbol. Okay, I am taking the a living symbol. Okay, with that this equation. Okay, so you will be getting a equation like this, right? You will be getting like a V pi minus I1 into 1 by j omega c mu minus V naught. I am taken this all minus term to the right side and finally got this equation. It is similar, same I am doing for other equations also. So similarly, when you want to find for respect to this next port, you apply in terms of anti-clockwise direction. If you apply in the anti-clockwise direction, P naught I1 and I2. So this is for port 2, right? So I2 into 1 by j omega c mu plus your V pi. So you will be getting this equation. Now, very interesting part. I'm going to draw this like I'm going to draw the model for this equation. So first let me put for this first port. So V pi. So you can see V pi. So this is a drop in the input port and the common port. And following that you have a current I1 with the for the capacitance C mu. So you have taken the capacitance, that is C mu. The reactance is 1 by it's a j omega, right? Right, in terms of reactance there, here in terms of capacitance it is written. Okay, so the current across the C mu will be I1 and the drop is V naught. The drop is V naught. With that your their input equation is drawn in terms of model. Similarly, you have to write for your output also, that is with respect to port 2. So V naught, you can see here V naught. So let me V naught. This is your for I this term and this term this one. So now we will go for the this equivalent part. This is what we derived, right? What I have done, I have separated using the Miller's network and I have framed the equation. From the equation I have drawn the model. With that you are getting this Thevenin's equivalent circuit. I hope you clear. Now, very interesting part. I am going to change this. This is a Thevenin's because you have voltage source and impedance and your voltage load part. Similarly, the right side also you have a Thevenin's equivalent circuit. I am going to convert the Thevenin's equivalent into the Norton's equivalent circuit because you should have only the dependent current source, so that I am converting into the voltage source into the current source, dependent current source. Okay, so you know the formula, that is I equal to V by R. So what is I have designated as ISC for converting into the Thevenin's to the Norton equivalent circuit. So what you will get, V pi divided by this reactance. So what is the reactance? 1 divided by j omega c mu. Okay, that is a V by R formula. With that it was written. Okay, so I hope you understand. This is a V and this is a R, V by R formula. Then this c mu, so that is a basic rule. When you are converting your Thevenin's to the Norton, this c mu will come parallel. So c mu will come parallel, you can see here. So here you have I2 current and the drop is V naught. So what is the understanding from here is your input should be always the Thevenin's part. Thevenin's part. Okay, the output should be a Norton's equivalent part. That is your understanding. I am going to fit this model. See, actually this is your circuit. Actually this is a circuit, right? Actually this is a circuit. So now what I am going to do, this is a C mu. For this C mu only we have done the Miller's analysis and we have framed this model. I am going to fit this model. I am saying again, I am going to fit this model in terms of C mu. If you fit, what you will get? You will get this, correct? So I have fitted this model. You can see it. See, C mu. You can see now. C mu, your C mu. V naught, V naught. Here I arranged like a. I will put it straightly. That's all. Both are same. Series. Here also series. Here you see this capacitance is parallel, and this is your current element. So current base character, that's all. So this is your simplified model, that is a small signal equivalent circuit including two port equivalent circuit model of capacitor C mu. That C mu was break into the two port in order to find what is the individual reactance of port 1 and port 2. Now I'm going to do some two interesting approximation to reduce the model still. Okay, so what I will do is I will say what I'm going to do is like I will remove this two element actually. I will remove this j omega c mu v pi and c mu from this model. I am going to remove these two. For that I am going to give the explanation. Okay, I am going to remove this two element from this model and I am going to draw the simplified another model. I am going to do the first approximation. The first approximation for removing the dependent current source. What is a dependent current source? What is a dependent current source? You can see here you have a two dependent current source. You have a two dependent current source, that is your j omega c mu v pi, and you have a gm v pi. Okay, this all both are dependent source, right? So I am going to consider as a equal. Okay, so what we are going to do is approximation 1. We can calculate the frequency at which the magnitude of two dependent current sources are equal. So with this typical values, I am going to proceed like a gm c mu with the other typical values. So the omega c mu v pi, this is a one dependent current source, and gm v pi is another dependent current source. I am going to remove this y, that is a question. So in terms of omega I have written 2 pi f c mu v pi equal to gm v pi. So you plug in all values. See, if you write this f, what you will get? F equal to gm divided by 2 pi c mu v pi will become cancelled. So you will be getting this equation. So if you substitute, your answer is 1.59 into 10 to the power 11 hertz. So that means 159 gigahertz. Okay, so the thing is, our BJT, that is a small signal bipolar transistor, so will work only in terms of megahertz. But here obtained values are in terms of gigahertz. It's a far very our frequency, our design transistor working only in the megahertz, but your obtained value in gigahertz when it is equal, both different sources are equal. That means it is not possible in the realistic system. So your transistor is not going to work in 59 gigahertz. You are going to work in the megahertz only. So that means it is meaningless to keep this current source. So I can remove this current source from your model. This is the first approximation. With that I am proceeding to the second approximation. The second approximation and interesting is what I am going to do is, so like a magnitude, that is your magnitude of the impedance, that is C mu is equal to RC parallel to RL. So this impedance part is your in the capacitance impedance I have written in terms of 1 j omega 1 omega c mu equal to RC parallel to RL. Okay, so you know omega equal to 2 pi f. Okay, if you rewrite, you will be getting this equation. Okay, f equal to 1 divided by 2 pi c mu into RC parallel to RL. See, when you substitute this typical values, so you will be getting 1.59 gigahertz. Okay, so this is also like a more far away from your working frequency, right? Your working frequency in terms of megahertz, but it is in terms of 1959 gigahertz. So what is the thing is your CMU will be greater than your this load part resistance when it is working in this frequency. Okay, so if your transistor is working less than your this frequency, you need to remove this CMU from this model. No, obviously this will be working less than this frequency only, right? The CMU will be greater than your RC and RL. So you have a higher reactance here compared to RCRL because it is connected in parallel. So you want to remove the higher reactance part, so that I have removed from this model. So finally this also removed and this also removed. So with that I will be proceed to the next part. Okay, so this is for approximation 1 I removed, and this is I removed for approximation 2. So with that 2 approximation you will be getting the simplified model. So this is your final simplified model. So you can see clearly I removed your one current source and C mu from this model. I have drawn the final model. Okay, I have drawn the final model here. I hope you are clear. So you can go through this equivalent model C mu V naught and C pi. So in right side you don't have a C mu, that is removed from the model. So now you can easily understand what is the concept of Miller's capacitance, why you want to do that such analysis in your emitter amplifier circuit. See, now what I'm going to do is I'm converting this, not converting, I am going to draw this entire thing as a CM. Okay, how? Okay, I'm going to reshape this model again. How? We will proceed with some equation part. Okay, so now let me apply the KVL. Okay, so when you apply, I want to find what is I1. Okay, so I will find I1. I1 will be a difference of the two drop V pi minus V naught divided by reactance. I'm repeating again. I want to find I1. So V pi minus V naught divided by this reactance. So you'll be getting V pi minus V naught divided by 1 by j omega C mu. So if you rearrange this equation, you will be getting j omega C mu V pi minus V naught. So obviously you are clear. Now I want to find what is the output voltage. You know output voltage equal to V naught I R. Okay, when you when you take this V pi as a 0, what happened? This also will become 0, and output this output resistance will be RC parallel to RL, right? So that is your output resistance, RC parallel to RL. So your current will be GM times of V pi. So that is your output current, output voltage. So V naught equal to GM V pi, your output resistance RC parallel to RL. Okay, minus will come because your collector current and load current both are opposite. By considering this direction, I am introducing minus here. So with this one coming. I hope you are clear. So this is I and this is your R. So with that, this is coming. Now I am going to substitute this V naught. Okay, I am going to substitute this V naught here. Okay, if you substitute minus gm v pi rc parallel to rl, so already you have v. If you substitute, what you will get, we will be getting this part. So I will take this v pi outside, this minus, I have another minus, it will become plus. You will be getting I1 equal to j omega c mu into 1 plus gm rc parallel to rl v pi. Okay, so this is the Miller's capacitance. Very interesting part. This is your Miller's capacitance. What is a CM? CM is nothing but a C mu 1 plus GM RC parallel to RL. So this is a impact of mu, that is a C mu in the input port. In the output port we are not considering. Though we are taking it is a considered higher reactance with respect to RC and RL in terms of higher frequency. So on the input side, the reactance of the C mu on the input side is C mu, that is C mu into 1 plus GM RC parallel to RL. So this is a Miller's analysis we have done for the common emitter amplifier circuit. So this is very important. This is CM equal to C mu into 1 plus GM RC parallel to RL. Further I am going to rewrite this equation. So you got like this, right? This is your equation you got. So I'm going to write this as a AV. You know already, AV equal to V naught by uh, like a VA. So you'll be having your V naught something like this, right? So GM uh, C parallel to RL. So you'll be having V pi as the input. So both will cancel. So I can write AV. AV is nothing but a GM RC parallel to RL. So with that, this was written as a AV. Okay. So Cm equal to C mu plus 1 plus Gm RC parallel to RL. So you can understand na? Gm RC parallel to RL means AV. So in order to explain that part only, I have explained this equation. Okay. So AV is nothing but a GM product of RC parallel to RL. So with that, this equation was remodified and written Cm equal to C mu into 1 plus GM RL. Okay, so consider two equation. Okay, so this is the equation we are going to use for solving the problem. It's a very important part. Okay, Cm equal to C mu into 1 plus Gm RC parallel to RL.